before I get there, let's do a recap of last session and kind of make sure that everybody kind of is on the same page on what we covered in the last lecture. So in the last lecture, we did robust machine learning and robust deep learning in particular, and kind of the idea was that deep learning models have gotten to very impressive accuracy today, right? So you read all kinds of media reports on deep learning beating human level performance, and that's far from true, right? It's far from true in any application, but it's especially kind of a concern because they're brittle, right? So humans are so much more robust than these machines are anywhere today. And you can see in these computer vision applications especially, it's highly brittle because simple perturbations, right, that are imperceptible to human eyes can drastically change the performance of these networks. And some of the examples we gave was, these, stop sign, if you just add like a small patch, or you add like kind of these artificial sunglasses on human faces, or you add like even noise that you can't even perceive, there are ways the predictions can drastically change. And one question was, can you incorporate robustness as a measure of performance, right? So you explicitly train your classifier to be robust, and that's where, there were two parts. So this was where it was a competitive optimization or a game theoretic setup where one player is the adversary. So he or she is really trying hard to fool the system, right? Introduce noise in a way so as to fool the system in the maximum possible way, and then the robust classifier will try to minimize that worst case loss. Right, and so here we said the standard ones right now have been these additive perturbations, and using very simple constraints like L infinity ball, right? So that means you're just saying element-wise there is some maximum amount of energy this noise can have, but there could be so many other better ones. So I think one open problem here is, what is the relevant perturbation that you should care about, right? In what way should you be robust? And that depends on the security concerns, right? That what kind of robustness you really want. Like, what does an attack mean in different applications? So it's not going to be one size fits all. Right, and that's, I think, the big open problem in this space is how to design an appropriate attack model, right? Because if we are going for perception, we can ask, if there is an explicit attacker who, when the human looks at the image, there is no perceptible noise, but then the machine is fooled, right? So that's one setting. But in another setting, you could say, there are specific kind of occlusions that could happen in the image, like people can go and blur out only a mask. Can I be protected against that? Right? Or it can be hardware faults, for instance. There could be faults in which the way the sensors collect data, and there are specific kind of like noise models that occur. So it's not even the worst case, it's some distribution that happens, and we want to be robust. So I think that's like the big open question here. What do we really design for? Right? And how is it going to be better in practice? So one is like the security threats, and there what we are lacking is what is the right attack model. The other is robustness being beneficial for machine learning on its own. Even if there is not an explicit adversary, can we still design robustness? And I think both are hard, because in the first one, we don't understand what kinds of security threats are relevant for machine learning. Right? In the second one, in addition to accuracy, what other measures do we really care about? What kind of robustness could truly help in the real world, right? And that's where we discussed there could be distributional shifts, like what you train on is different from what happens in test. You want it to be critical to safety and other concerns. If it's an autonomous drive, right, you want it to be especially good when it comes to rare scenarios like accidents, right? So that may not happen 99.99%, but it's that remaining percent that you really care about, right? So the robustness can mean that, but how do you truly design for those rare scenarios? That's hard to specify, right? So if you look at that autonomous drive scenario, how do you translate that risk of an accident to this kind of a worst case, right? That translation of that specification is still hard. And that's why it's still an open problem. So I think that's where the field is at today, right? I mean, we're doing very simple things like this L infinity loss, and that kind of, you're doing it locally or updating. If you remember, we covered this fast gradient sign method, and then just updating the neural network based on this, the worst case loss, right? So this was more a local method, and then there were these global methods that were more based on convex outer bounds, saying I'll ensure I will be robust to some convex outer bound of my output, right? So no matter what perturbation is there within the set, I can still be giving the right prediction. And with all these, with especially these convex methods, the computational cost is a big concern, right? So these can only now run at the level of MNIST or barely CFAR, right? So they are definitely not at a scale you can run on ImageNet or bigger data, bigger models. There is just no way these are currently scalable. And one is just pure compute. I mean, we can write better software, have better compute, but at the same time, this is a very expensive operation, right, to come up with these outer bounds. And so if there are ways to approximate it better, like not make it exactly convex, but have even approximations of that, that's an open problem. And I guess right now the biggest drawback with all this we saw was it is really poor in generalizing to test data in an adversarial sense, right? Like if I really looked at evaluating my test samples also in an adversarial loss, right? I used the adversarial loss criterion. The generalization gap is so huge, right? And this is kind of happens again and again in almost every example. And the question is why, right? We seem to be avoiding overfitting for the general IID setting, right? So we saw CFAR, ImageNet, all these examples. If the train and test are just evaluated on accuracy, it's reasonably okay. There's still a gap, but that gap is quite small compared to here, whereas it seems to be grossly overfitting to training data when you add this robustness. And why is that? Right, so I mean, there's currently no generalization theory that also accounts for both the explanation of these models doing well in the accuracy sense, but not in the robustness sense, right? I mean, you can think of some intuitions that it's much easier to fool the network in an adversarial sense, but not in an average sense, right? But that's still not enough to explain why the gap is so huge, right? So that's an open problem. And it's also unclear if for these over-parameterized networks, do they also get more and more brittle as you increase these networks, and is there a theory to explain that? We currently don't have that, right? Because one intuition is as these networks get really big, so if you're like using these minimum norm ideas we talked about in the previous class, right, it's still like you're hoping stochastic gradient descent and these algorithms can minimize the norm even while interpolating on the data. So in the average sense, in the sense of accuracy, they generalize well. But in the adversarial sense, right, it could still be very bad, right? Because you could still make adversarial perturbations and result in a bad error. So there's still no theory behind that, and I think that's one big open problem if you want to look into these set of problems. And the other open problem was this data, right? So there is the hypothesis that these in order to achieve robustness, you need a lot more data than just accuracy, right? So first of all, even to get accuracy, we are needing to go to these large data sets, right? So, I mean, we needed something like ImageNet to even have any practical application of computer vision. I mean, until that number of classes and that number of training examples, it was just not practical enough to have a working computer vision system. But then if you're asking for robustness, we are expecting like potentially even, you know, a lot more, even possibly exponentially more samples for robust loss compared to just the standard accuracy. And so this is now an issue, right? So how do we get these samples? I mean, it's like, is it just that we will keep needing more data as these models get complex, and there's just no other way to get robustness? Right? That's again an open problem. I mean, is it just that we inevitably need this much data, or are there ways to overcome that? Right, so that's kind of the summary of the previous lecture. Any questions here?
Actually, regarding the performance, I have a question from last time. When we talk about the x plus a delta, which we add some noise to the infinity number, in the test result, it says that the robust COMNET performs better than the conventional one. But in this case, we see that performance is actually a worse situation. There is a kind of gap.
When did we say it's better than the conventional?
Yes,
in that one?
That, if the conventional one is to some extent 0.1, but in the
in the adversarial loss sense, right? So it is certainly going to be, you know, if your evaluation is again an adversarial loss, if you have a classifier with no robustness criterion, it's going to be really poor, right? So robust classifier will be better than that. But what we are now measuring is between the train and test what the gap is.
So here is no kind of adversarial.
It's both are adversarial, right? So I mean, both on training you're looking at adversarial loss, on the test you're looking at adversarial loss for the same classifier. Whereas in the previous lecture when we compared classifiers, we compared the standard classifier to the adversarially trained classifier. And so the standard classifier is going to be much poorer than adversarial one, right? Because it's not going to be robust.
Okay.
Right? So there are two different issues. One is like standard classifiers by themselves are brittle. So unless you add this robustness criterion, it's going to perform very poorly, right? But the other is, it's still hard to get this itself. I mean, so this is much better. So this test error in the adversarial sense is going to be much better than a standard classifier. Maybe standard classifier will be even lower. But then, you know, compared to the train, this is going to be still low, right? So that's the two different issues at hand. Does that answer?
Oh, okay, yeah.
Any other questions? Yeah, so I would say this is much more of a nascent area compared to standard machine learning. So I think there are just a lot of interesting problems here. So from here, we can now, you know, given that data is becoming ever more important, right, we'll now make the segue to data to ask how we can improve our dependence on data, right? Because I guess that's been the shift from classical machine learning to now modern machine learning. In the classical setting, the data was what we had, right? So classical statistics assumed we had very small amount of data, and so we would have extremely small models because there was just no other way around it. Whereas now with the availability of the internet and all the data collection processes in place, right, the infrastructure in place, now we can ask for more data, right? So in many settings, it's possible to get more data, but there's going to be a cost to it. And so that's where the trade-off becomes a lot more interesting. But the question is, in many applications, it's still very expensive. So can we reduce the data and still get good performance? What are ways to do that? And I think in general, data is like the hidden part of the equation, right? Like when people think about AI and machine learning, the outsized emphasis is on algorithms, right? Like trying to have like a secret sauce or this magic that would really boost performance. And also we as researchers tend to design more on the algorithmic front, right? We're always thinking of new algorithms, better algorithms and methods. But in practice, in so many settings, what really matters is data, right? I mean, compute also matters, but that I think these days, at least in many applications, is more of a cost perspective because more hardware is going to be expensive. But at least in many of these applications, compute has been resolved to a big extent, but data is not, right? I mean, data is much harder to obtain. You can't easily scale up except for these web scale applications where there are already data collection process. And so in order for machine learning to have impact beyond just the standard applications that we see in these big IT companies, I think the design of better data dependence and also better ways to collect data is going to be the next big question, right? So, and this is where I think we need better research as well to ask how we can build intelligence into this data collection process. So not just design algorithms to process data, but also to collect data better. And that's where I think there's so many open problems, and today we'll try to kind of look at an overview of that and then focus on active learning. So how many of you here have used, have you tried to collect data yourself? So what are some examples? Like what was your kind of process of collecting?
Used like any Turk to other people to annotation something.
What was the application?
For the cell type,
okay.
Cell center detection.
So this was a single cell detection one. And what was surprising to you? Was there some lessons you learned that you want to share?
The lesson I learned is that a human in that platform is not reliable, which means different people perform differently even on a certain data set, and even with the same person, the performance varies maybe according to their mood or their intention, their focus. So as a result, you have to evaluate the result properly so that to make sure the data is to some extent usable. Otherwise, it could be even worse than computer generated. Yes.
I mean, that's a very good point, right? Like, and this refers to the label noise, which we alluded to in some of the previous lectures. And in the next lecture, we'll go into some models for that and some more details of how to overcome that. But also, what about the cost? I guess even like having a human annotate every cell in an image probably took a long time, right? What was like the size of the image and how?
You have to design a kind of algorithm, so that which means you can minimize the points. We call it the points ratio, which means how many points over how many percentage of a pixel in one image that you have to make a person to label. And the ratio, the lower to some extent will be better. So make available in what sense? Can you?
Which
means if originally if you would like to make the person to, for example, to draw a boundary, then this could be very expensive because theoretically you let the people to annotate larger percentage of the pixels out of all the pixels on the certain image, so that this could be expensive. So if we can lower we call the percentage that is label pixel over all the pixels, then
Right.
we can lower down the cost.
Yeah, I mean, this is called like the landmark annotation, right? Because instead of like labeling every pixel, maybe people put some landmarks and then the algorithm tries to join them in like the best possible way, either some kind of curve fitting algorithm or in some other examples, maybe polygons, right? Like if it's like a bounding box, maybe polygon is okay, but for the cell, it has to be a curve, and then you kind of have some algorithm to overcome that. And I guess, and that's where, I mean, you're using like kind of some more intelligence into the process, right? So you're not just giving to the annotator what is needed to be annotated. Right? Instead, you're using another intermediate algorithm to fill in the gaps rather than asking the annotator the full information. Right? So that's one instance of doing that. And then in general, the question is here you're kind of having the human intuition or some other extra knowledge to design this curve fitting algorithm. Right? But are there ways that the machine learning by itself could figure out how to fill in the blanks, or even ask what are the most appropriate questions, right? That's where I think what I mean by intelligence into that process. So there was some other, yeah.
Can you define what you mean by data?
Good question. What, or what is the source of confusion in terms of what's your definition?
I mean, I use satellite data, and I have hundreds of thousands of satellite images.
Yeah.
Would you call that data? Or
Certainly. I mean, anything, I mean, in the context of machine learning algorithm, it would be like, what's the input to the algorithm?
I mean, does it have to, are you looking for something where I've actually labeled the images, some supervised learning?
Right.
Is that what you're calling
Yes,
it?
yes, label data, right? So currently we are, so far we've only been looking at supervised learning, and after the next class we'll move to unsupervised and generative models. So when I mean by data in this context, it'll be the labeled data, which is much more expensive than the unlabeled data. And I was curious in terms of some lessons learned or surprises when people try to collect their own data, maybe label them, right, so on.
So the labels would actually be metadata for the data.
So if it's already available, that's great, right, if the metadata, but if that's something manually that needs to be annotated, that's when it becomes a lot more expensive and a lot more labor intensive. So I was curious if people had some, good experiences to share or bad experiences to share from that process. Like this, like the example with mechanical Turk. So did anyone else have to deal with that? No. And that kind of speaks to the field, right? Like we mostly work on benchmark data sets because it's a lot more convenient for us to start there if our focus is on developing a new algorithm or trying to argue why one algorithm is better than the other. So that's where a lot of researchers are focused. And I think in order to have a big gains, especially in many real applications, there are a lot more open problems on the data side, which also require algorithmic design, right? Like designing better algorithms to collect data is what I think is the missing piece. So I encourage you to think more for algorithms for making the data side as well intelligent. Right, so one is like with annotating the data, and that's what we will focus on, but even the other issue of like how do you get your unlabeled samples to begin with is also an important one, right? And that speaks more to like the imbalance in data, the biases in data in terms of different categories, especially gender, race, and these other biases that some of the researchers working in fairness have been uncovering. And I'll try to give a glimpse of that in the next lecture. But for now, let's more focus on how to, given like a pool of data, how to kind of work with it and then potentially collect new data samples based on what the model has learned. Right, so that's what we'll focus on today, but there are many broad questions on what data quality, how it has implications on the end results. right? And if you connect it to the previous lecture, we talked about the data poisoning attack, where it was an attacker trying to poison data, and even a few examples could drastically change the results on next, right? So that's the extreme case. So you can imagine if even there were more kind of benign biases, that definitely has an impact. And what makes this challenging is to think about this at a huge scale, right? If we have millions of samples, you cannot go and inspect these samples. If you have thousands of classes, you can't go and even inspect class-specific performance in a detailed way. And so the scale is what also makes this really challenging to assess these qualities. But we'll table the quality issue for the next lecture, and here we'll focus on especially the supervised setting and how we can reduce the sample complexity. And some of like the state-of-the-art systems, right? At least the open source systems. I mean, in the companies, these are going to be even several orders of magnitude bigger data sets available for some of the tasks. I mean, ImageNet we saw is 1 million plus. If you go to the full ImageNet, that's actually 14 million images. These for speech recognition, you have like, the state-of-the-art is about like 11,000 plus hours. I think this is also a bit dated, so it's even bigger now. And for NLP, this NER is called named entity recognition. I'll talk about the task a bit later, but that's like about 600,000 annotated words. Right, and these are some examples. I mean, if you go to some of these big companies, it's going to be even a much bigger scale. Right, you can think of hundreds of millions of images in many settings that will be trained on, and then you can also go to videos, and the scale multiplies. So that's where the cutting edge of the field has headed in deep learning, but this is not within reach in every application, with every researcher, with every domain, right? So what is the alternative? And these are, I think, some high-level ways to overcome the data dependence and reduce our requirement for big data. So the simplest one that researchers already do is data augmentation. So if you're running any of these computer vision algorithms for deep learning, right, there are some standard augmentation code that's already available in these standard packages. And what they do is simple things. They may like slightly clip the image, they may slightly rotate it, add some like random noise. So there are ways to kind of, like take one example and effectively multiply it to more examples, right? So you're making variations within your given examples, and the idea with this is then you can avoid overfitting to the given examples. Right, so in a way they're trying to incorporate robustness in a much more heuristic and simple way compared to the robust deep learning we saw. So that's kind of the standard approach, ways to augment the data, but there could be also more sophisticated approaches for augmenting data where you can use some knowledge.
Are you saying you're augmenting the data by creating more data points that are perturbed, or you're just perturbing the data points?
So by perturbing the data points, there are effectively more data points.
Okay, so you do that on the training set,
right.
Not before you split it to training and testing. Because a few lectures ago you talked about the issue of having like many images being very similar, and how that could mean that like overfitting can be good because the same image can show up in training
yes.
and testing. So
I mean, in that setting, right, it was a bad data set construction.
Yeah.
So let's assume the data set is constructed in a good way, but all this you can only do in your training and potentially validation, right? I mean, testers, by, according to if you're going true to machine learning, you should never touch the test samples ever, right, during your training.
Yeah, so but you would want to do that before the validation, like before you split it. Sorry, after you split it into
yes.
training and validation, not before.
Yes.
Otherwise you would create this problem.
Yeah. And so the idea is you can, try to avoid the brittleness issue in a simple way, right? So if you can perturb like locally, or at least hoping that it's still kind of invariant with these small perturbations and simple changes, right? So, and so this is like standard now in these deep learning packages. So if you're doing any of these standard deep learning model, it's already inbuilt there. It's, it's a line of code. But there could be data augmentation in more sophisticated ways, and this is again an open problem, and I'll talk about some of these in the upcoming lecture, right? Because one idea is, the domain expert has some additional knowledge that's not directly incorporated in these deep learning, right? Deep learning is purely data driven. What additional domain knowledge should you incorporate? For instance, if it's the example of a walking robot or a Segway or any kind of robotics application, there are laws of physics, right? We know gravity, there is, the mass acceleration, we know those equations. So somehow we should already incorporate and not try to learn everything from scratch. Right, and that's where deep learning, and especially, if you're looking at deep learning on gameplay, they tend to focus on purely data driven, but I think in many applications, the interesting thing will be combining the two. And also the other project we have on drones with the neural lander also combines this knowledge, right? So there are many more sophisticated ways to do this, and we'll cover some of this in the next lecture. And then you could do semi-supervised learning. So this is also we'll cover after the generative models. But the idea is if you have lots of unlabeled samples and few labeled samples, how do you use both unlabeled and labeled samples? Right, and so this is kind of now saying, don't try to label everything. Even if you have just unlabeled samples, can you directly use them and improve your machine learning? So you could do transfer learning. So you have the pre-trained model, you now transfer it to a new task. In fact, this is the most standard way computer vision is done, right? And even other areas, but especially in computer vision, there is a big pre-trained ImageNet model that's available in the open, and then researchers usually start there and try to transfer it over to other tasks. So again, there's going to be challenges, because if you're looking at cell data and try to transfer it from ImageNet, it's probably going to have really poor performance. Right, so then, the domain adaptation is a much more sophisticated extension of transfer learning. Right, there you're explicitly accounting for the fact that there is a shift in the way the training was done and the shift in distribution to where it's going to be tested or applied on, and we'll cover this in the coming lectures. So I just gave a brief summary, but we'll kind of go into the details of all of this in the upcoming lectures, but the one we'll focus on now will be active learning. Right, so these are like broad categories you can have to cope up with limited amounts of data. Any questions here? Or did I miss some category? So let's now look at what active learning means and how we can use this to reduce our data dependence. Right, so some considerations there. We'll see like active learning really has to be, you should have this ability to interact. Without that, you won't be able to do that. So these are just some considerations, right? I think they are pretty obvious. But the active learning, what it's saying is don't collect all your data to begin with, right? You really want to collect your data as you go along, as you're performing your training. And so the idea is you start with a beginning set of training data, you train a model, but then you ask the model to select new unlabeled samples. And then you send it back to an oracle, typically a human annotator, and then you repeat this process again and again. So this falls in the area of interactive learning, because you're assuming there is an interaction process. Right, so it's the other line of work is called passive learning, because you just have a set of samples, you're passively learning with this. Whereas in the active setting, the model is actively choosing what examples it thinks will benefit it the most. Is the difference clear? So there are lots of applications of active learning, right? So I took this slide from Yushing, who gave a talk at the AI for Science workshop. I hope at least some of you were able to attend his talk, or the afternoon session was all focused on active learning. So it's, I think I don't need to convince you that there are lots of interesting applications possible if you can have active learning, right? Because in many cases, it's possible to interact with the system. I mean, if you're discovering a drug, there's going to be some actual wet lab experiments that need to be done, right? So you can pause those experiments until you analyze the data and decide what experiments to run next. And in fact, it's done even today, but mostly through human intuition, right? It's usually the PI saying, okay, maybe this is the most promising route to experiment next. How can we automate that? So this is kind of called adaptive or automated experimentation, because now based on all the data I have, I can decide what new molecules to test for being effective as drugs, right? Because there are just billions of molecules. I can't go and test each one of them. What is the most promising ones? And same with material science, protein engineering. So there's just so many areas for application of active learning. And at Caltech, I think it's probably the most used form of machine learning across campus, right? So there are lots of great examples. So if you're looking to apply this, I think this is a great place to do that. So that's like the brief kind of motivation from the sciences, right? So if we now go into the details of what are forms of active learning, right? So there are mainly three different types of active learning. So the pool-based one will be the most commonly used. Right, so in the pool-based, what you do is you have one pool of data, you use it to train the machine learning model, and then the machine learning model selects a new pool to be labeled, right? So pool or batches. So you're like saying this is one pool, train the model, then go back, label another pool, and so on. And this is also the most effective, right? Because most of the time the data labeling will be offline. I mean, it will take a lot longer to go and run an experiment in the wet lab, right? The machine learning algorithm will come up with an answer in no time, right? So because this latency for getting answers from the experiments and getting labels is so intensive, the pool-based makes a lot of sense. Right? Or even like with Mechanical Turk or any of the annotation platforms, it's going to take time. Right? It's going to be much harder to engineer having a human be online and give you answers with guaranteed latency. Right? So given that, I think this is like the standard thing to do in many, especially scientific applications, because the data labeling is a very time-intensive process. So the second class is known as the stream-based sampling, selective sampling, or active learning. And there the idea is the data is coming in a stream. You have to like say each sample, I'm going to like now label this, or it's going to go away forever, right? You're not going to, in a stream-based setting, you can't possibly store all of this. This is way too expensive. So you have to make a decision online. Should I label this or not, right? Otherwise you lose that sample forever. Whereas in the pool-based, it's usually a fixed set of unlabeled samples. You have like this, all the collection of molecules that's available, right? And within that collection, you're making further decisions. Whereas in the stream-based, it's just streaming data and you lose it if you don't decide to label it. And there are lots of examples of stream-based settings, right? If, you look at like satellites and the kinds of sensors that they have, the data they collect is way too expensive to be stored or even transmitted back to Earth in many settings. And right now, some way the decision is made what to store or not, right? And or in like kind of lot of web-based applications, if you have like billions of queries coming in, right, you can't possibly store all of them, right? You may store some interesting ones for more offline inspection on those. And so this will be more at like very large scale dynamic data, right, coming in very fast. It's much more, that's where this is applicable, but those applications are much rarer, or much kind of availability of that scale, especially for academic researchers, is harder to obtain. And that's why there's more interest in the pool-based setting. So the third one, the membership query, is very relevant, but also the least studied and much harder to analyze in theory and also in practice, right? So what does membership query means? It's more like asking the oracle, usually the human annotator, to come up with an example in a certain category, right? And so this is very applicable if you have rare classes. Right, so let's say like, we were talking about autonomous driving, right? If you're just looking at all these examples from the data collected from a drive on the road, right? Most of them will be benign incidents, right? Like they won't be like accidents, which is what you really care about. So then maybe you could ask human annotator to try to describe what an accident looks like, right? I mean, the challenge here is you can't easily like kind of recreate the scene. Then we have simulators then that try to recreate the scene, right? So it's much harder to come up with a construction of a realistic looking sample that belongs to a certain category or has certain specifications, right? I mean, this I think will be the much more relevant one in the upcoming years, but also the least studied one. So we won't talk much about this, but keep in mind, this is where I think the field will be heading in terms of especially safety critical applications or anomaly detection, all these instances where you really want to go and look at the hard, rare examples, right? So if you just collect your data, the unlabeled data in a passive way or in a IID way, you cannot hope to get a lot of examples of this, right? So same with like hate speech, or fraud, right? Like there are, if it's unlabeled, you're unlikely to come up with a lot of examples of this. But then humans have intuitions of what these examples could be, and it's most of the time it may be even experts, right? That's the other big challenge with these membership query-based models, because you may need like a real expert to construct and describe this. And the other challenge is they may describe it in their own words. How do you put that into a realistic looking sample into the data set? So this is where the challenges are, and it does relate to these simulations, right? Many times you cannot directly construct that data sample you're after, right, or these rare classes you're after, but then you may use like a simulator to try to simulate those samples, but there's going to be a domain shift. Okay, so these are all the challenges with the membership query. I will mention though there is an interesting work by Daniel Xu and his collaborators that shows that these membership queries can be much more powerful than active learning, right? They could have exponentially better sample complexity than active learning in some examples. And that's not surprising, right? Because it could be sometimes much more informative to come up with examples that are very valuable to the algorithm than the algorithm having to pick in a limited pool, right? So, so there is theory saying that this will be valuable, but trying to make this practical is a big challenge. Any questions here with these three types of active learning? So have any of you used active learning in your research? No one? Angie, you have used, or you work on active learning.
One comment.
Yeah.
So for the pro-based sampling one, not necessarily you will have to sample another pool. It can be, okay, you have a big pool and start with,
Right.
and just work with that pool and try to sample.
Right.
That's
Right.
most useful.
Right. Right. Yeah, that's a good point, right? The pool refers to the fixed set of unlabeled samples. And then like the batch, I mean, I guess that's more called the batch, the size you subsample, and that could be even one in a special case, right? But many times it makes sense to have like a bigger batch. Yeah, that's a good point. But yeah, but I guess you also work more on the pool-based setting, right? And the research in the other two are much rarer.
Yeah, and in terms of what kind of application it is, their research like you can put this in the sample classification measurement organization. In the stream one, you need to discard a lot of samples.
Yes. Yeah.
And then for this one, that is
Right. Yeah, because the stream is much harder, right? Once you say I'm not going to label it, it's gone forever. And but on the other hand, here the cost is not in terms of like unlabeled samples. You have infinite number of unlabeled samples in principle, right? But what the cost is in terms of the latency of the decision, right? You can't possibly store all of it. You have to make this online decision whether this is even worth storing and labeling.
So in terms of what is more expensive in that case, and all I can hear because student access is not very expensive and then it's okay.
Yeah. Yeah. Any comments, thoughts here? I think this is the very important slide, right? Because it gives the overview. So let's kind of now dig a bit more, mostly in the pool-based setting, right? We'll focus on pool-based. So one question will be this acquisition function. So that'll be the criterion used to select this new set of samples, right? Like what is the criterion that you will use to decide what should be the new pool of samples to be labeled, right? And then the other is the batch size. We were asking how many samples do I select to be put out for labeling, right? I mean, the idea is maybe in a wet lab you have many different tables available, so it's not just one experiment, you could do many experiments in parallel, so you'd rather do many of them, get the results, because each one takes time. Right, and then the other is like, and especially with deep learning, this is going to be a lot more relevant, is once you have your new set of samples, do you take your old samples and new samples and train everything together from scratch again? Or do you just fine tune or have a way to incorporate the new samples in a more incremental fashion? Right, you use your previous pre-trained model and have ways to incorporate the new sample. And you have to be careful here because there could be catastrophic forgetting, right? Especially if you have a large set of new samples, you could forget what you learned about the old samples, right? And usually people mix old and new samples in some distribution and try to update it. So these are more right now tricks and kind of heuristics rather than a definite theory of what's the most efficient way to mix this, right? Because the traditional active learning was just assuming you retrain from scratch. You just take all your data, both the old and new data, and retrain from scratch, but that's just way too expensive with these deep learning models, and so people come up with ways to incrementally train where they use the previous pre-trained model, but have some strategies to mix old and new data in mini batches and keep kind of training further your existing model. Does this make sense? So now the main, I guess, question is what is the acquisition function, right? That's usually like the biggest design question, because what is the criterion I use to select new samples? And so in most of active learning, the uncertainty-based sampling is the most prominent method, and it kind of makes sense, right? Intuitively, you want the samples which are most uncertain for your model to be labeled. Right, so if you're most uncertain on a sample, right, that's when you ask the human for the correct answer. If you're already pretty certain on this sample, right, there is no benefit. And that's kind of the intuition too. If you have like just a passive data set of a lot of cats, right, you get pretty good at the cat classifier very quickly, and so it doesn't help you to have more cats, especially in the same angle, in the same pose. Right, and so here, if you're doing it actively, you can decide that, oh, I've already learned this pose and this kind of cat now, so I'm pretty certain on this kind of examples. Now let me go and look at new latent attributes and new categories where I'm more uncertain. And so now the question is, within uncertainty, how do I think of it, right? What is a measure of uncertainty on my samples? And so the most kind of common one, right, is called the least confidence sample. So if you have like a softmax classifier, right, so if you're using your DeepNet, the last layer is softmax, right, and so you would be getting like a soft output. So for each category, you can like look at the output of the softmax as a measure of confidence. Right? So there are downsides to it, and we'll come to it in a minute, but you can ask which one has the least confidence, right? So you will always pick the highest softmax as your category, right? So you will look at the max, and then you will like kind of, I mean, that's the y hat, right? And then you will like look at the sample where you have the least confidence, right? Because in your softmax classifier, you're picking the topmost category and you're looking at what is the value of that. And whichever sample has the least, you will pick that sample first to be labeled by the human. Right? And you could do like a softer measure. I mean, in the least confidence, you're only going for the top category, right? Whereas in the entropy measure, you're looking at all categories, right? So think of it as, in some cases, maybe you have like this top category here, right, with fairly good confidence, but then there are many other categories with even quite a high confidence, right? So in this, and if there are like especially thousands of categories or very large number of categories, there's a lot of mass in this rest of categories, right? So you're ignoring that if you only look at the confidence of the top category, because in that case you're saying both these are the same, right? So you could have one instance where a top one, sorry, there is, you know, like the way it's distributed, right? So you could have like the second top to be also very high, or you could have like it distributed among all the categories, right? You're not distinguishing the two when you look at just the least confidence, because you're only looking at the confidence of the top category. So the entropy is like a softer measure because it's also considering all the other categories. And so this is like, these are used if you only look at the frequentist setting, right? So if you're having a standard deep neural network, in the last layer will be the softmax, and you would use that. But it turns out like a much better strategy is to have a Bayesian model and like, you know, essentially have a way to sample different answers, right? So you're sampling multiple times, like what the label should be, and then based on the disagreement, you're kind of looking at measure of confidence, right? So the detail is really whether, you know, when I look at my uncertainty, do I do it in a frequentist model, or do I do it in a Bayesian model, right? So why does this matter, right? So, you know, what is really am I obtaining by doing this kind of Bayesian method for active learning compared to the frequentist? right? And especially the softmax. So with these softmax classifiers, it's been known that they cannot model this, what is known as this epistemic uncertainty well. So if you look into the uncertainty quantification literature, right? So if you ask Andrew Stewart, for instance, there is a lot more detailed decomposition of error, right? It's not just error. What are the different sources of errors matter a lot. And if you look at the two broad categories, one is known as aleatoric errors, the others are called epistemic errors. Right, so the aleatoric errors are those that is just not explained by data, right? So, these are like hidden, like even if you had more data, you would just not be able to explain it. So in this curve here, for instance, right, like these blue dots here are the training points, right? So it ends up that you're only collecting your data in part of the curve, right? You only have your data around here and around here. So that's more like the data collection you're not having in other places, right? So that results in epistemic errors because that's due to limited data. On the other hand, this gray space here, the gray part of the region is aleatoric because even if you collected data everywhere, you would still have that uncertainty, right? So there is just like, even if you kept collecting data, there is some uncertainty you can never reduce. And then the epistemic, if you collected more data and had a better model, you would be able to overcome those uncertainties. Right, don't worry about the details. This was kind of picked by a paper that was looking at a better quantile regression, but more focus on the curve, right? I think this kind of nicely picks up the point that, there where the data is more prevalent, there the epistemic errors are small, right? Because you have more data and more evidence there. Whereas the parts where the data is unavailable, right, these pink points, that's where there is more epistemic error. And within aleatoric, there are kind of two different forms of error. It's homoscedastic if it is just uniform for all data points. Right, heteroscedastic means it depends on the data, but that's more a detail of what are the kinds of errors within that category. But the main important thing is to differentiate this epistemic and aleatoric errors, right? And what these softmax classifiers are known to do is not be good in really accommodating for these epistemic errors and giving you a true measure of uncertainty, right? So there's a lot of evidence that they are poorly calibrated. So calibration means they're giving you the right level of confidence, right? So if this classifier says I have 90% confidence, that means if you're like sampling kind of 100 times, 90 times it is correct, right? But that's kind of many times not going to happen because there's no, the way we train it and the way we are designing these softmax classifiers make them not have the right level of confidence. And for active learning, this is going to be pretty crucial because if they're not giving you the right measure of confidence, then you're making mistakes in saying which sample should be labeled. Right? Because for those that are not labeled, you're accepting the result from your classifier. Right? So think of an extreme case where the classifier is making mistakes but is extremely confident. Right? Then you will not go and ask the human for any new label. Right? So you will just keep with your existing model and never update it. So that would be a bad setting, right? You don't want that to happen. And that's why it's crucial to have models that give you right scores of uncertainties. And so the figure on the right is what the softmax classifier is, right, the standard neural network. And you can see here, I mean, these black points are again the training data. So the training data is more in the middle part of the curve. Towards the end of the curve, there's no training data. Right, so and the softmax classifier, even though there is no training data here, has very limited uncertainty, right? It has pretty high confidence even on those parts of the curve, right? So it's not able to model epistemic uncertainty well. Whereas the left one we will see is a Bayesian model. I'll come to the details of what that model does. It has a much better measure of epistemic uncertainty because it's not seen data at these extreme parts of the curve, so it is a lot more uncertain on those parts. Right? So is this distinction clear between epistemic and aleatoric errors?
So the model can output the blue region, which is uncertain.
I mean, you can always ask the model to kind of complete the curve, right? And you can always ask what is the uncertainty in any region. And so the deep learning model, the standard frequentist one, believes it has low uncertainty in these parts of the curve, even though there was no training data there. And that relates to also kind of one is poor generalization, but this is kind of a level above that, right? It's saying, how are you even, do you know that you're making errors here, right? And in many cases it doesn't. And in fact, the deeper the network or the more nonlinear the network, this problem gets worse, right? It tends to get more and more overconfident as you try to make these networks bigger. And that makes sense because you're trying to, in a way, fit more to this limited data, right? So if you don't have data everywhere, this is going to be a huge problem. Is this clear?
What happens if you increase the degree of your model so that you get closer and closer to overfitting, so that the data away from where you have data, the curve will vary a lot more? Will you do a better job on your epistemic uncertainty?
No, that's the thing, right? It may actually get worse because it's seeing a lot of data points and fitting very well. So it may end up expecting to fit even other data points well, even though it hasn't seen in that region.
But the curve will vary a lot more when you get away from where the data are.
Yeah, but it hasn't seen examples there, right? I mean, that's what a good model is supposed to do that. But, if you're just doing a standard softmax classifier, it doesn't do that well. That's the problem. That's what we want to solve. We want it to be the curve like the left, but that's not what you would get. Yeah.
But couldn't you just very slightly perturb the data and then see that the curve in the outer part changes a lot and just show that it's unstable? What should happen is that the curve far away from the data should be very unstable, right? So could you just, with a small perturbation of the data, see that curve flip the other direction and then effectively see that there is uncertainty on the left?
But that's what somehow you have to do some kind of post-processing or something else. You have to fix this confidence issue in some way, right? The question is, how do you do that? And if you're thinking of this perturbation, that's precisely what these Bayesian models do, right? They will try to sample this.
You don't need to perturb, right? You have derivatives in a neural network, so you can maybe just look at derivatives, right?
But you do want to randomly perturb it, right? So there has to be some randomness. I mean, without randomness, you would not kind of be able to tell, right, what happens there. Right, and that's what the Bayesian models now, the question is, how do we do that in a good way? Yeah.
So in this case, in the frequency model, you can also add something explicitly saying do not extrapolate to the
Yes, yes.
all those things.
Exactly. I mean, the standard softmax, you won't get this, right? And then there's a whole line of work which you can say, can I calibrate this better, right? In just the frequentist setting. The other option is to have a Bayesian model with explicit kind of, additional stochasticity that can, hopefully get much better at detecting this epistemic uncertainty. Right, so that's kind of the two lines. So we'll, talk a bit more on the Bayesian one, but there is a whole line of work even in the frequentist case. So yeah, so now what do you do to get this Bayesian neural networks cheaply, right? I mean, the name of the game will be like to do it cheaply. I mean, if you are having 100 layers with even up to 1 billion parameters, there's just no way you can, put an arbitrary prior and sample from the posterior, right? So what do you do that's quick and simple, right? So papers in the beginning mostly focused on a very simple form of stochasticity, which is just dropout, right? So in dropout activations, what you're doing is you're looking at each activation and, independently just saying whether I should set this to 0, right? I just drop out that activation. And so you could use that as a way to get like an ensemble of models, right? Because now if you are dropping out, you're kind of looking at all these combinations of different models that can happen based on zeroing, any number of activations. So that's more an ensemble rather than a single model, but you're able to cheaply sample from this ensemble, right? That's what makes it efficient. And so what you can do is you can like now do different samplings of the dropouts, so you get different results in the end, and you can compare the results, right? So you can say how many times they agree, how many times they don't agree, and based on that, compute the confidence. Right, so there's a simple way to introduce additional stochasticity and kind of, look at like now variations, right? In a way you're perturbing and asking how much is the result, changing. And the hope is, and the idea is, if you train the network well, it will still be robust on where there is a lot of training data. But if there's very little training data, then with these perturbations, you would have a lot bigger changes, and based on this disagreement, then you reduce your confidence. Right, so you can get a better measure of confidence based on this simple dropout mechanism.
Does it mean here we only have access to one training sample, but with different dropout masks? So which means we estimate for one input, we'll have different.
Yes. Yeah. So you keep. That's why it's like more the ensembling, right? You think of it as many different models evaluating on each sample. And there's a cheap way to get the ensemble because you're just having a very simple independent probability to mask out or drop out different activations. Right, so a more sophisticated way is to put the uncertainty on the weights instead of the activations. Right, because now you could say instead of like fixed weights, right, the weights are parameters we optimized for accuracy in the frequentist setting. In the Bayesian setting, I could say each weight I have a prior distribution, and now given the data point or the batch of data points, I can update and have a posterior, and I'll sample from the posterior. Right, so that's a Bayesian setting on the weights where, I put a prior distribution here and then I sample from the posterior given my batch of data or mini batch of data. Right, again, the challenge here is the scale, right? We can't put any arbitrary prior distribution. We can't hope that that would scale to even any moderate sized networks. And so the one simple trick here is like called Bayes by backprop. It's kind of a simple variational approach. It's an approximation to the full posterior and using a very simple prior distribution of independent Gaussians that will enable us to make this reasonably scalable. Right, it's still not going to be efficient on the largest networks, but it is definitely better scaled than the general one. right? But this is kind of the two parts, right? I guess the frequentist versus the Bayesian, I hope everybody here is already comfortable with, but I'm just reiterating, right? If you're doing the frequentist setting, you will want to optimize the weights for just the conditional distribution of your label given the input, right? That's all you care about. Whereas if you're looking at the Bayesian setting, right, one estimate is this map or the maximum a posteriori estimate of your weights, which looks at the posterior distribution and looks at what is the mode of that posterior distribution, right? And the posterior, of course, can be decoupled into the prior and the likelihood, right? So that's the standard Bayesian setting. Right, so that's the two differences here. There is a prior and you're looking at the posterior, whereas in the frequentist, you're just looking at the optimal set of parameters based only on the likelihood. Right, and this kind of prior is this additional stochasticity that you hope can better incorporate the epistemic uncertainty. Right. And so, of course, computing the actual exact posterior is intractable for, even any most settings, right? We would almost never do the exact posterior, and that's where the variational approximation is the most common one. I hope many of you have probably seen variational approximation, but just a quick run through is instead of the actual posterior, you're now trying to find another distribution Q that's a good approximation for the posterior, right? And the important thing is that, is like kind of a much simpler distribution that Q compared to the actual posterior, right? And that doesn't depend on the data, so that you can easily sample from it. So this is very important. And the next two kind of things are just expanding that, and then there is the prior part, there is the likelihood part, right? So this is kind of the standard expansion. And but even computing this kind of, this expectation is a bottleneck, right? So this is going to be expensive. You can't kind of really compute this at scale. And so the other thing what people do is make approximations. Right, so instead of like doing the exact minimization, you could instead say, because if you see the KL distance, that's also an expectation over Q, right? And the second term is also an expectation over Q. So instead of first computing the exact expectation and then minimizing, you can just like look at taking a gradient step, right? And you can approximate, you can like essentially reverse the order, and under continuity, this is okay. Right, so you first differentiate, then you take the expectation. Right, so this is the kind of the standard variational tricks where you now operate on the gradients instead of exact expectations. Any questions here? How many of you have worked on variational approximations before? Really? Okay. Or how many of you have seen this in a course before? Okay, so I think this does warrant an entire course by itself, right, if we go into all the tricks. But I hope at a high level you can see that the main important thing is to approximate the posterior. The posterior is hard. We'll instead find another distribution parameterized by theta to approximate it. But even computing the scale distance is also hard, right, because it's an expectation. And instead we'll exchange the expectation and the gradient step and go back and forth. Any questions here?
What is theta here? Because we know D is the data, right?
Yeah.
So P W given D is a kind of
the posterior.
Yeah, the posterior based on the real data.
So theta
will approximate it with Q, right?
Yeah. So theta will be new parameters. I'll give an example. So it will be, for instance, a new distribution with new parameters, right? So think of it like could be Gaussian exponential. So you come up with a distribution where some parameter is what you will optimize over. Right? Is that clear? Yeah, so we will, I will kind of give a bit more details in the upcoming lecture because I didn't realize, I thought this is something that you've already covered in other courses, but we can kind of delve into the math in the next lecture. Let me leave it at that because it may take a bit more time. So we'll come back in the next lecture, but I hope at the high level, the aspect that was made here is we are now making the weights stochastic instead of being fixed. Right, that's the high level idea. And then the idea is that can give a much better estimate of the uncertainty. Right, so let me conclude what we saw in this lecture. Within active learning, we looked at 3 forms of active learning, right? The pool-based one is the most standard. We said it's a fixed pool of unlabeled samples, then we'll go batch by batch on what to label. The stream-based was where it's a stream of data, you have to decide what to pick or you lose it forever. And in the example-based one, you're asking the human annotator or the oracle to come up with examples of a certain specification, right? And we saw the pool-based is the most common because it's the easiest to implement. And then we said for pool-based, what makes sense will be a notion of uncertainty, right? Like samples that you're most uncertain about, that's what you should go and ask the human. And that's when we got into the issue of how do you measure uncertainty. If the model doesn't have a good measure of its own uncertainty, that's a huge problem. And that's where we had these 2 sources of errors, the aleatoric and the epistemic. The epistemic was the error when there is limited data, right? Or the model itself is making mistakes, but deep learning models in general, the standard ones, the standard softmax classifier based ones are poor in terms of detecting these epistemic errors. Right, so where there is limited data, it still tends to be pretty highly confident about its answers, and that's what we wanted to overcome. And the Bayesian setup is much more amenable to incorporating these epistemic errors because the intuition is if you now perturb in those regions where there is few samples, your answers are going to be much more different. Right, and that's the notion of disagreement because now if you think of an ensemble of models and these models are giving you very different answers on an example, your confidence should be lower. And with these Bayesian models, essentially you're getting an ensemble, right? And we saw this simple dropout-based system where you're just dropping out activations. So through this, you're getting a cheap way to get a huge ensemble, right? Because you're getting all these different combinations of on and off of the activations. And so you can use that as a way to look at disagreement and come up with more robust measures of uncertainty. And then the more sophisticated way was to do a variational approach on the weights. So where you put a prior on the weights and instead of the exact posterior, you're making approximations of the posterior. So in the next class, I'll kind of take a bit more time to explain the variational approximation since this may be the first time some of you are seeing that. And then we'll go into all the deeper issues in active learning. So we'll continue on active learning. I think it took a lot longer time than I expected. Thank you.